Hi guys, there was a request in class on Monday on how to do problem 2.74 from the uh, homework 2. So I'm just gonna kind of quickly go through how I would solve this problem. We have a pole vaulter is nearly motionless as he clears a bar set 4.2 meters above the ground. He then falls onto a thick pad. The top of the pad is 80 centimeters above the ground and is compressed by 50 centimeters as he comes to rest. What is the magnitude of the acceleration as he comes to rest on the pad? So if we're drawing a picture, we're talking about a pole vaulter who's going over um, um, going over his obstacle. The problem tells you that you have he's up here at an initial height of 4.2 meters. Down at the bottom, you have his landing, and this thing is at 80 meters above the ground. But he only ends up compressing the pad by 50 meters. So his final height would end up being 0.3 meters above the ground itself. Unfortunately, you can't just go from this initial height to this final height as it is, because there's two separate pieces of the motion. So the first piece is while the pole vaulter is in free fall. So it starts at the 4.2 meters. It has a velocity of 0 meters per second. While he's in the air, experiencing acceleration of negative 9.8 meters per second squared. We have some amount of time that's going to happen. He's going to no longer be in free fall. Once his height reaches the 0.8 meters, that'll be when he starts touching the pad. And then you'd have some final velocity that you don't know. So that brings us right here to the top of this, pad. So we can go and solve that piece. Maybe I'll label it as like A. So if we solve part A while he's in free fall, the thing that we really are most interested in trying to figure out would be this final velocity, because whatever this final velocity would then become the initial, would end up being the initial velocity that exists for while he's being slowed down by the pad. So these two velocities will be the same. It'd be the final velocity from the free fall, but the initial velocity of him coming to a stop due to contact with the pad. So if we're trying to find the final and we don't have time, then our velocity squared equation is where we need to go. So the final velocity will be equal to the square root of the initial velocity squared, which is 0, plus 2 times the negative 9.8 meters per second squared, times the delta y, which would be a final position of 0.8 meters minus the initial of 4.2 meters. I'm going to get out my calculator, so give me a second. So put these values in. And we get a final velocity plus or minus 8.16 meters per second. It's traveling down though, so this v final really needs to be a negative 8.16 meters per second. So then that can be updated in the second part of this problem. So the second part of the problem, right, our initial velocity is the negative 8.16. The initial height is going to be the 0.8 meters. The acceleration that we're experiencing, we don't know. That is our, that's the thing that we're looking for. We don't know how long it takes for him to come to a stop. We know that his final height will be the 0.3 meters that will allow a compression of 50 centimeters. And then our final velocity, he's coming to rest, so 0 meters per second. Okay, so then this is the second constant acceleration problem that we need to solve. We're now looking for acceleration, and we don't have time. So we can actually use the same equation that we just did. The final velocity squared equals the initial velocity squared plus 2a delta y, except for now we're solving for a. I'm going to do that first. If we solve for a, we're looking at the difference of the velocity squared divided by 2 delta y. Final velocity is 0. Initial velocity is the negative 81.6 meters per second. Divided by 2, and then our final height is 0.3 meters minus 0.8 meters. Punch that into your calculator. And I find an acceleration of 66.64 meters per second squared. And I will just double check real fast in Mathstream since I have it open. And that ends up being correct. It asks for 2 sig figs, so the acceleration would be 67 meters per second squared. Okay, so for this problem, the real, challenge here is really acknowledging that there's 2 separate problems that have to be solved. You have a free fall while the pole vaulter is in the air, and then you have a constant acceleration problem where he's being stopped by the pad. So you just have to kind of work both of those problems and then use that shared bit of information about the final velocity of the free fall is the initial velocity of the slowing down from the pad. Hope you found that helpful.